All right. Hello, everyone. Welcome to another GBO Science Lunch Talk. Today we have Dr. Trey Wenger, who is from the Dominion Radio Astrophysical Observatory, where he is a postdoc. And today he will be talking to us about the structure in the Milky Way using galactic H2 regions. So, whenever you're ready, take it away.
Thank you, Jesse. Thanks for that introduction, and thanks for the invitation to give a lunch talk today. It's always great talking to you fine people. I see a bunch of familiar faces there. I think the last time I gave a talk in Green Bank was about a year and a half ago. It was right after I finished my PhD, and I talked a lot about the projects that I worked on my PhD and some of the follow-up projects that I was working on. But today, for this science lunch talk, I thought it would be more fun to give a much more informal talk about a lot of the projects that I'm currently working on and showing a whole bunch of preliminary, very cutting edge results, and mostly just for discussion. So throughout this talk, feel free to interrupt and ask questions, or if you raise your hand, your virtual hand in the Zoom, I can see that, or write a question in the chat if you'd like to, but by all means, let's make this a nice interactive talk. So as Jesse said, my name is Trey Wenger. I'm a Covington postdoctoral fellow at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia. It's quite cold up here right now, but in the summer it's very beautiful. And if this pandemic ever ends, it would be great to have some of you come visit. So today I'm going to talk a lot about my research. I'll give a little bit of motivation and background, and then I'm going to talk about 4 different projects. One is a search for new H2 regions in the southern sky, and then 3 kind of science projects that I'm interested in using these H2 regions. And the big overall motivation for this work is that I'm interested in constraining the structure of our galaxy, the Milky Way. And this is important because it tells us something about how the Milky Way formed, how it evolved, and how galaxies form in general. The Milky Way is a laboratory that we can study in detail that we can't find anywhere else in the universe. We can study the structure of the galaxy from the smallest scales to the largest scales, which just isn't possible outside of the local group. Now, when I talk about galactic structure, I'm really talking about 3 different kinds of structures. The first is kinematic structure. How is stuff in the Milky Way moving? What is the galactic velocity field, for example? The second thing is the metallicity structure, the chemical structure of the galaxy. How are the heavy elements distributed? And what can this tell us about galactic chemodynamical evolution? And then finally, and most dear to my heart, is the morphological structure. For example, galactic spiral structure. Does the Milky Way have well-defined spiral arms or not? And what can we learn about those spiral arms that to then tell us about the formation of galactic spirals in general? And so these are the 3 kinds of structures that I'll be focusing on today in my talk. And the tracer that we use to look for galactic structure are H2 regions. You could use anything: stars, neutral gas, molecular gas. People have done all kinds of things. But the objects that I'm going to talk about today are H2 regions, these classical tracers of galactic structure. Just as a reminder, an H2 region is a cloud of ionized gas that surrounds recently formed high mass stars. So these are O and B type stars that have formed in the past 10 million years or so, that heat up their natal gas surrounding them, causing it to ionize and become what we call an H2 region. Here's a very nice picture of M20. On the left is a visible light picture, where in red you're seeing the H alpha, so that's really tracing the ionized gas there. This blue stuff back here is a reflection nebula. On the right, this is an infrared view of the same H2 region. In red is 24 micron MIPS data, and in green and blue are 8 micron and 3.6 micron IRAC data, really showing you this typical infrared characteristic morphology of an H2 region, which is the heated dust grains in the center. That's what the 24 micron emissions really tracing, surrounded by the polycyclic aromatic hydrocarbons, the PAHs or the PAHs, which is tracing the photodissociation region that surrounds the H2 region. And this is a very typical morphology of a classical H2 region, and that will become important later on. So I mentioned that H2 regions are these classical tracers of galactic structure. People have used H2 regions to trace structure in both the Milky Way and other galaxies for 100 years. And I think that this picture of the Whirlpool galaxy really highlights that. So this is a visible light picture of M51, and in red is the H alpha emission, which you can just see with your eye is concentrated, mostly in the spiral arms, with a few interarm H2 regions for sure. But the biggest, the brightest, and the most of the H2 regions are concentrated in the spiral arms. And so you can use H2 regions to delineate spiral structure in these galaxies. And the goal is that if we can find all of the Milky Way's H2 regions, then we could do this in the Milky Way as well. There's other reasons why H2 regions are great tracers of galactic structure. First, and probably most importantly, is that they're extremely bright, especially at radio wavelengths, where H2 regions are among the brightest objects in the sky at about 10 gigahertz. On the left here is a GBT radio continuum map of an H2 region, just showing how crazy bright that these things could be. This is NGC 7538, by the way. And then perhaps equally importantly is that H2 regions have a characteristic spectral fingerprint. They have a way to easily identify them amongst all of the gaseous nebulae in the universe. Namely, that's the recombination lines. And so if you find a recombination line that's telling you that there's recombining atoms, it's telling you that there's ionized gas, which means what you're looking at is an ionized gas ball, and it must be an H2 region. There's other spectral spectral lines that you can use to fingerprint these objects. Collisionally excited lines in the infrared and the optical, for example. On the top right here is a spectrum. This is a GBT radio recombination line spectrum at about 10 gigahertz. So whereas H alpha is the transition when an electron is recombining with a proton and the electron jumps from the third principal quantum state to the second principal quantum state, that's H alpha. Radio recombination lines are the same transition, but at much higher principal quantum states. So at about 10 gigahertz, we're looking at electrons that are jumping from about the 100th energy state to the 99th energy state. So much lower energy, longer wavelength transitions, but it's the same atoms recombining. Other reasons that H2 regions are great galactic structure tracers is that we can measure some of their physical properties just based off of the spectral line and radio continuum observations. I'll be talking a lot in this talk about electron temperatures and metallicity. So the electron temperature you can get just from some fundamental physics arguments from the radio recombination line to radio continuum ratio. And then because the electron temperature is empirically correlated with metallicity, since the metals are the dominant coolant in an ionized plasma, there's an empirical relationship where a more metal-rich plasma is more efficient at cooling and will thus have a lower temperature, a lower electron temperature. We can then infer the metallicity of these objects. Or if you're observing collisionally excited lines in the optical or the infrared, you can derive the metallicity directly, of course. And I put here that this is a zero-age metallicity, and that's kind of an important point. H2 regions are young, they're newly formed, they only live for a few million years. And so when you see an H2 region and you measure its chemical abundances, you're getting an instantaneous snapshot of the abundance in that part of the galaxy today. This is in stark contrast to something like stars, which have some unknown age. They migrate around the galaxy throughout their lives. So it's much more challenging to infer, the present day chemical structure from stars, if not impossible. Whereas with H2 regions, that's what you're getting. You're getting a direct measurement of the present day abundance. And then finally, H2 regions are good galactic structure tracers because we can get their distances in different ways. So if there's maser emission, you can actually get a maser parallax measurement and get a trigonometric distance that way. If it has O stars that can be seen by Gaia, you can get a trigonometric parallax distance that way as well. In all other cases, you can get a kinematic distance by assuming some model of galactic rotation and measuring its radial velocity from the spectral line, for example, the radio recombination line. I'll talk a little bit more about that later. So I hope I've convinced you that H2 regions are a great tracer of galactic structure. And then now I hope I can motivate you that if we want to use H2 regions to trace galactic structure, we need to find all of the H2 regions. We need to complete the census of galactic H2 regions. And by doing so, we'll be able to pin down these structures and then also do some other interesting physics that I won't talk too much about in this talk. So for example, deriving the H2 region luminosity function, which is important for understanding high mass star formation and the initial mass function, for example. And then also, if you can find all of the Milky Way's H2 regions, then you can directly measure the high mass star formation rate of the galaxy because you're finding all of the high mass stars that are forming or have recently formed. So there's some other cool physics that you could do with a complete census of galactic H2 regions beyond the scope of what I'll be talking about today. On the right here, this is a galactic longitude velocity diagram. So on the y-axis is galactic longitude, just the position along the galactic plane that you're looking. And on the x-axis here is line of sight, or LSR velocity, so the radial velocity relative to the local standard of rest. And this is a great plot for galactic structure because these are the two measurables when you find an object like an H2 region, or you're observing some gas like H1 or CO. You can just plop it down on this diagram, which is showing both of the observables, and then try to infer some galactic structure from it. So this is what the H2 region longitude velocity diagram looked like in about 2010. There were about 900 H2 regions known in the Milky Way. And we could tell just by looking at this plot that the census was incomplete. There were parts of the galaxy that just didn't have any H2 regions where we thought there ought to be some. I can tell that by looking at this plot, but for those of you who aren't familiar with longitude velocity diagrams, let me just dissect it a little bit here for you. If you assume a flat rotation curve, so you assume that the orbital velocity of stuff in the Milky Way is basically constant with galactocentric radius, then the longitude velocity diagram can be dissected quite nicely into some different pieces. So for example, on the right here, this is a cartoon of the Milky Way where I've put the sun here at this yellow circle and the galactic center here at this red circle. And then I've color coded these different parts of the galactic plane and then color coded the associated parts in the longitude velocity diagram. So for example, here in the first quadrant, which is between 0 and 90 degrees longitude, if you have a positive velocity, you're in the inner galaxy, which is this kind of blue semicircle here. And that corresponds to this part of the longitude velocity diagram. Whereas if you have a negative LSR velocity, you must be in the outer galaxy, which is the green part of the diagram here. And the second quadrant, only negative velocities are allowed. So they shouldn't find anything here at positive velocities in the second quadrant. And then the third and the fourth quadrants are just the symmetric inverse of the first and second quadrants. And so with that in mind, you can kind of start to do a little bit of galactic structure with this LV diagram right away. So for example, you can see quite clearly that there aren't many H2 regions here in the green part of the LV diagram, which is to say that there aren't many H2 regions out here in the outer part of the galaxy in the first quadrant. And so that was our first hint that maybe the census was incomplete because we expect there to be H2 regions there. There's plenty of molecular star-forming gas there, so there should be some star formation going on there. And then second was that if you just count up all of the H2 regions, there were about 900. That's far less than what we see in some other external galaxies that are Milky Way-like. So the census was incomplete, and it was time for us to go find the rest of the H2 regions. We were motivated to do this by some recent advances. So first was the Spitzer and Wise galactic plane and all sky infrared surveys, which we thought were sensitive enough to identify all of the all of the H2 regions in the Milky Way based off of their infrared morphology. So we thought that we could find all of the things that looked like H2 regions, basically. And the second was that we had some amazingly sensitive radio telescopes like the GVT that we could use to go out and detect the radio recombination line emission from all of these candidates to prove that they are in fact bona fide H2 regions. And just based off some back of the envelope sensitivity calculations, it was clear to us in about 2010 that we should be able to find all H2 regions in the Milky Way that were ionized by at least a single O star. And that was what motivated a lot of this work. So the next two slides, I'm going to summarize a decade of work. So first, we had to go find all of the H2 region candidates in these infrared surveys. And these ended up being compiled in this thing called the WISE catalog of galactic H2 regions, which is just a catalog of all of the infrared identified H2 regions and H2 region candidates. These were identified by eye, and the sources in this catalog are grouped into several categories. So before our surveys, there were about 1,000 known H2 regions that are in this catalog, 2,500 candidate H2 regions. These are things that have the infrared morphology of an H2 region, and they also have associated radio continuum emission in galactic plane and all sky radio continuum surveys. And then there were 4,000 what we called radio quiet candidates. So these are objects that have the infrared morphology of an H2 region, but they either weren't detected or the radio continuum surveys didn't cover the part of the sky where those candidates were. So this is, and you can play with the catalog at this website if you like to. It's pretty fun. So we had a big list of catalogs. We proposed for a whole bunch of telescope time on both the Green Bank telescope and the Arecibo telescope to carry out what we called the H2 region discovery surveys. These were surveys at about 10 gigahertz X band, where we observed several, usually about 8 radio recombination lines. that we could then stack together to improve our sensitivity. We observed about 1,000 H2 region candidates from the WISE catalog, and we more than doubled the number of known H2 regions in the northern sky over about 8 or 10 years or so. So here on the left, this is just a typical GBT spectrum, radio recombination line spectrum towards one of our H2 region candidates. And here on the right is the longitude velocity diagram, now including in magenta all of the H2 regions that were discovered by our northern sky surveys with the GBT and the Arecibo telescopes. And so as of about 2018, there were about 1,800 H2 regions, which is about twice as many as there were before we started. But it's clear from this diagram that we missed a part of the galaxy. There's a big chunk here between about 340 degrees longitude and 240 degrees longitude where there aren't any magenta points. And that's, of course, the southern, the part of the Milky Way that's only viewable from the southern hemisphere. And that'll be the motivation for the first project that I'll talk about, the Southern H2 Region Discovery Survey. Are there any questions about the background and motivation section? All right, we'll just push on then. So the first project that I'd like to talk about is the Southern H2 Region Discovery Survey. And as the name implies, this is just an extension of what we did in the Northern Hemisphere with the GBT and Arecibo into the Southern Hemisphere, which was trying to find some new H2 regions in the southern sky. We used the Australia Telescope Compact Array, which is a 6-element compact interferometer located in the Australian outback. We had a 900-hour survey over about 4 years. And although the collecting area is quite a bit less than what we were able to get with the GBT and Arecibo, for example, we make up for that by the amazingly broad bandwidth that the CAB backend of the compact array has. And so we were able to observe from 4 to 10 gigahertz, 4 gigahertz of instantaneous bandwidth, which allowed us to observe 20 radio recombination lines simultaneously, which we could then stack and improve our signal to noise quite a bit. This is a big survey with a bunch of collaborators. You might recognize a few of these faces. There's this guy here, Will Armentrout. I hear he works for you guys now. The results of this survey were published in 3 papers. The most recent one was the full catalog, which was just accepted and is on the archive as of a couple weeks ago. So now I can finally show you the results of those and say that they're the final results. Just briefly, I'll show you some of the data. It's an interferometer, so it's kind of cool. We get to make images. That's something we didn't get to do with the GBT or Arecibo. So we can get much better estimates of the continuum flux densities, for example. So here are a couple of our compact array images, our ATCA images of some of these new H2 regions. The yellow circles here are the WISE catalog positions and sizes. So that's where our infrared targets were. And then the background here is just the 9 gigahertz radio continuum flux density. So in total, we targeted 435 H2 region candidates, and then about 200 previously known H2 regions, just so we could get some better data than what we had previously. And in fact, we detected more than what we targeted. We detected 436 candidates and 206 previously known H2 regions. And so this was the first project that I was a part of that had a greater than 100% detection rate. That was kind of fun. In the full catalog, we publish all kinds of intermediate data products. For example, we publish the continuum flux densities in 256 megahertz spectral windows. And so that allows us to derive things like continuum spectral energy distributions and fit spectral indices. We also reduce the data in full Stokes. And so there's full Stokes maps of some of these fields. Here's just a gallery of some of our radio recombination line detections. We had a great sensitivity that allowed us to detect the recombination line towards so many of these H2 regions, but also for some of the bright ones, we were able to detect the helium and the carbon recombination lines as well. We do have a few weak detections, of course, and we have very few, but there are a few blended detections where it seems to be that there's multiple radio recombination lines along the line of sight, either due to confused discrete H2 regions or perhaps even due to diffuse ionized gas along the line of sight as well. And then again, in the full catalog, our most recent data release, we publish a bunch of intermediate data products, including Gaussian fits to all of the individual radio recombination line transitions, not just the stacked, the 20 transition stacked spectrum. And so this allows us to, for the brighter sources where we have good sensitivity to detect the recombination line and individual transitions, it allows us to do things like calculate the line to continuum ratio as a function of frequency, look for departures from LTE, and things like that. So it's a very rich data set, so that I'm excited that we can finally have the opportunity to mine for all of its things that it's going to be able to tell us. So just in summary, like I said, we discovered recombination lines towards 206 previously known H2 regions, but these are detections that are much better than the previous Parkes single dish measurements. And then we detected recombination lines towards 436 H2 region candidates. So this increased the number of southern sky H2 regions by more than 100%. We more than doubled this number. And some back of the envelope analyses in this paper suggested that the H2 region sample is complete to about 250 millijanskis continuum flux density across the Milky Way galaxy. So I think we have, for the first time ever, we have a flux limited sample of H2 regions in the Milky Way. And so this is going to allow us to do some really cool science, I think. Here on the right, this is the longitude velocity diagram now. In magenta are our northern sky H2 regions, and in green are our southern sky H2 regions. And we have just discovered so many new H2 regions that you can't even see the original sample on there anymore. It's pretty fun. So just a couple of interesting highlights, things that we've already found in the SHRDS or things that we're doing right now. So we seem to have found a previously unknown population of what appears to be rotating H2 regions. So here on the left, these are two moment maps of a newly discovered southern H2 region discovery survey H2 region. The top is the first moment map. So this is showing the radial recombination line velocity across the H2 region. And on the bottom is the second moment. So it's showing the line width, the full width half maximum line width. And what you can see in the first moment is that there's a velocity gradient from the one side to the other. And in the second moment, there seems to be essentially peaked line width. The middle panel here is showing just the uncertainties in those quantities. So you can see that the gradient from one side here to the other is about 10 kilometers per second, whereas our uncertainty in any one pixel is much smaller than that, less than a kilometer per second typically. Similarly, the magnitude of the increase of the line width is much greater than our uncertainty. And on the right here, this is just a really simple naive model of a spherically symmetric rotating ionized plasma. So we just stuck in a ball of ionized gas, let it rotate, and then took a synthetic observation, and this is what we found. The top again is the line velocity, and the bottom is the line width. And what you can see is that other than the rotation on the sky, the gradient and the line width profile kind of seem to match, which might suggest that what we're seeing here is actually a bulk rotation of the entire ionized ball. We're also exploring other explanations, for example, outflows. And this work is very preliminary, and hopefully we'll get a paper out about this sooner rather than later, so that we can get some theorists on board to help us understand what in the world is going on. I'll just gleam over this in the interest of time, but we're also obtaining some H1 absorption observations towards a bunch of these H2 regions as a way to resolve the kinematic distance ambiguity and get accurate distances to these nebulae. This is a project that's being led by a previous co-op student of mine, Aidan Mackay from the University of Victoria. We observed for about 200 hours with the Australia Telescope Compact Array to obtain H1 absorption spectra towards a bunch of these H2 regions. And we expect that we'll be able to resolve this kinematic distance ambiguity towards about 100 new H2 regions in the southern sky, which will allow us to make a face-on map of the locations of these H2 regions. So that's all I wanted to say about our southern sky survey. Are there any questions or comments about that? All right, so now I wanted to just move on to three little research topics or research projects that I've been working on recently that are related to our southern sky survey, but maybe just adjacently. So the first is galactic kinematic structure, trying to understand the velocity field of the Milky Way. And so this was motivated by Mark Reed's 2019 paper as part of the Bessel Maser Parallax survey projects, where they published the parallaxes, radial velocities and proper motions of about 200 high mass star forming regions in the Milky Way. And in the paper, they do a bunch of analysis trying to fit spiral models to these H2 regions to make claims about galactic spiral structure, which is all fine here. But what I'm interested in more so is what the full phase space information of these maser sources can tell us about the galactic velocity field. So on the right panel here, this is a face-on view of the Milky Way, where the sun's located at this dot. The galactic center here is down at the origin. The points here are all of the maser sources that have parallax measurements from this paper. And then the vectors show the peculiar motions. So these are the motions that can't be explained by the rotation curve that they derived. And here you can see the magnitude. This size here is about 50 kilometers per second. So there's quite a bit of peculiar motions going on. These maser sources are kind of doing a bunch of weird things. Some of this structure is well known. So for example, here in the Perseus arm, which are these black points here, it's been known for a while that there's some peculiar motions going on there that can't be explained by galactic rotation. So this is interesting, and it's important to understand this because the kinematic distance method relies on having a good understanding of galactic rotation. So if your galactic rotation model is wrong, then your kinematic distances are going to be wrong, and your mapping of the velocities to the distances is going to be wrong. And so I think that using this information, using the peculiar velocities that we can actually derive, because we get the full phase space information of these maser sources, is going to significantly improve our ability to derive kinematic distances for the sources that we can't get this full phase space information for. So right now I have a student, Isaac Cheng from the University of Waterloo, who's working with me on this project. Just a couple of days ago, he generated these fantastic plots that show an interpolation of the peculiar motions of these maser sources across the galactic plane. So the left panel here is the peculiar motion in the radial direction. That's the U component of the peculiar velocities. The points are all of those maser sources color-coded by their peculiar motions, just from that plot I showed before. But the new and interesting thing here is that the background color is an interpolation between those discrete maser points. This is called kriging interpolation. So now we can map out this velocity field and maybe apply that to our kinematic distance method. The right panel here is the same, but it's for the circular component of the peculiar velocity field. And so you can see there's quite a bit of structure here. I think the scatter in the maser points exceeds what we're kind of seeing in the map, but maybe the map is giving us a good average. And so now the question is, does incorporating this peculiar velocity field into the kinematic distance method actually improve the kinematic distances? And so just yesterday, Isaac generated the fantastic plot here on the right. This is showing a cumulative distribution function of the difference between the kinematic and the parallax difference relative to the uncertainty. So the idea here is that if your kinematic distances and your parallax distances are giving you the same answer, then this distribution should be centered on 0. And if this uncertainty is a good reflection of these differences, then you would expect this cumulative distribution function to follow a normal distribution. So the plot here on the left is some previous work that I did for my PhD, and this was published in 2018, showing this quantity for all of the maser sources that were known at that time. So all of the sources that had a parallax distance for which we could derive a kinematic distance. And what we found back then was that although the shape of this cumulative distribution function was pretty Gaussian, it was pretty normal, which is telling us that our uncertainties are doing a good job of representing the differences. What was bad, or what was worrying, was that there was a systematic offset, which was that the kinematic distances were always over predicting the parallax distances. And this was basically unexplained at that time. Now what Isaac has found is that by incorporating the peculiar motions and then using an updated galactic rotation curve and a whole bunch more maser sources now, this cumulative distribution function looks a lot better. So it's a lot closer to being centered at 0, which is saying that our kinematic distances are doing a much better job of predicting the parallax distances. And the shape of the curve is still pretty normal, although we seem to have a bunch of outliers up here that are as of yet unexplained. But again, this is very preliminary, hot off the presses as of yesterday. And so I'm excited to see where this project goes and what we can learn about the galactic velocity field and how these will end up improving kinematic distances, not only for H2 regions, but also for other gaseous tracers like H1. Any questions about galactic kinematic structure? That was a pretty short section. All right, we'll just keep pushing through here. So the next project I wanted to talk about was galactic metallicity structure. So this is the idea of using H2 regions to map out the chemical structure of the Milky Way. People have been doing this for a long time, both with H2 regions in the optical and also in the radio. On the left here, this is a paper that we published many years ago now, 2015, using GBT and 140-foot observations to derive the electron temperatures for a bunch of H2 regions, and then using this empirical relationship between the electron temperature and the metallicity to then infer a metallicity. So here, this panel on the left is showing a face-on view of the Milky Way, where the sun is located here at the red cross. The galactic center is here. These black bars are meant to represent the long and the short galactic bars. The points are all of the H2 regions for which we were able to derive electron temperatures and infer metallicities. And then the background is an interpolation of the metallicity, here represented as the oxygen abundance across the galaxy. So what we found in that paper was that there was a radial metallicity gradient. The metallicity is higher in the center of the galaxy and lower on the outskirts. This is a well-known phenomenon that's easily explained by top-down galactic formation models. But what we found that was interesting and unexpected was that there was azimuthal structure in the metallicity gradient. That is to say that the gradient in some azimuths, for example, in this direction, was steeper than it was in other azimuths, for example, in this direction. And this was basically unexplained because our understanding of galactic chemical evolution is that as the galaxy spins, it's like stirring chocolate chips into your cookie batter. After a few swirls, everything should get really well mixed, and you shouldn't have any azimuthal structure like this. Chemical evolution models of the galaxy typically don't expect, or don't predict azimuthal variations, or they don't assume azimuthal variations, and they just assume everything's axisymmetric. So this is interesting and kind of unexpected. And around the same time and recently, people have been finding similar trends in external galaxies. And so here on the right is a picture of, or is a map of NGC 2997, another galaxy, where they used optical emission lines to derive the oxygen abundances for a bunch of high mass star forming regions. And here they've color coded those regions based off their deviation from an axisymmetric radial gradient. So they subtracted off a radial gradient to show you these deviations. And what they find is in some parts of the galaxy are more metal rich, and in some parts of the galaxy are more metal poor than what would be expected from symmetry. And in this paper, they make some claims for the relationship between those features and the spiral arms in this galaxy. So this is kind of interesting, and it seems like it's real. So we should probably investigate this a little bit further. So a couple of years ago now, we published a paper where we had a VLA survey of a bunch of H2 regions that we handpicked to be kind of uniformly distributed across the galaxy, visible by the VLA. The idea here is that we could then make a more complete and homogeneous map of the chemical structure in the galaxy. And then we chose to use the VLA for this experiment because we would get images and therefore much better continuum measurements, much better line to continuum ratio measurements, and then much better metallicity inferences, therefore. So here on the left, this is kind of the big result of the paper. This is a map of the Milky Way again with the sun at the red cross, and here's the galactic center. The points are all of the H2 regions, and then the color and the background is this Kriging interpolation to get the metallicity across the galaxy. And we find basically the same as what we found with the previous single dish map, or the single dish measurements, which is that we find this radial metallicity gradient and crazy azimuthal structures. Here on the right is a way to kind of quantify those azimuthal structures. This is showing the slope of the metallicity gradient, the slope of the oxygen abundance gradient, as a function of galactic azimuth. So 0 degrees here is going from the galactic center towards the sun. You can see we have a fairly shallow gradient in that direction. And then as you move to higher azimuths, which is going to the right here. So for example, at 90 degrees azimuth, which is going from the galactic center to the right in this plot, you have a very steep negative gradient. And so there's statistically significant azimuthal structure here that's worrisome for our understanding of galactic chemical evolution. So my previous co-op student, Age Metallicity from the University of Victoria, has been exploring this with our new data, with our Southern H2 Region Discovery Survey data, now expanding our map of galactic chemical structure into the southern sky. So here on the left, this is the radial metallicity gradient that we derive using the full census of galactic H2 regions now. So this is showing the oxygen abundance as a function of galactocentric radius. And the gradient that we fit, including the entire sample, is basically what other people have found using young stellar tracers like open clusters, and then of course H2 regions. All right, this is a preliminary plot. This is a longitude velocity diagram, but here we've colored coded the H2 regions by their oxygen abundance, and the points are really small, so they're kind of hard to see. So this is an avenue that we're exploring. What can we learn about galactic chemical structure in the LV plane? Distances are hard to derive. Kinematic distances are notoriously inaccurate. So what can we actually learn about galactic chemical structure in this plane where we don't have to rely on distances? And so I'm just showing this plot because I think it's interesting. We haven't quite figured out what we're going to do with it yet. So if you have any ideas, please let me know. But what Aidan has done so far is he's mapped out, for the sources for which we can derive kinematic distances, and we think that they're fairly robust. He's mapped out a face-on view of the H2 region oxygen abundances across the galaxy. So for the first time, this plot here on the left is showing the distribution of H2 region metallicities across the entire Milky Way. So here's the sun at the star, the galactic center here is at the origin. The triangles here are our northern sky survey data, and the circles here are our new H2 regions from the southern survey. And it's hard to interpret this plot. We still need not a lot of work to go here, but I think it's safe to say that the azimuthal variations that we're seeing persist in the southern sky. Here on the right is a preliminary plot trying to show that. And so this is again showing the slope of the oxygen abundance gradient as a function of azimuth. And you can just see it kind of varies wildly. So there's certainly something funny going on. I think we need to pin this down a little bit better, make sure that we're understanding the uncertainties properly, and then we can begin to explore some of the theories for what might be causing this. Is it related to spiral structure? Is it related to interactions with Magellanic clouds? What's going on here? Is it something that has to do with the bar and streaming motions? Yeah, it's a lot of work to be done here, but I think for the first time with this full galactic map, we can actually answer these questions robustly. All right, we made it to the final topic, which is my favorite. Are there any other questions before we get here?
Trey, I'd just say that we should probably try and get to the end of the talk in the next 5 minutes.
All right, I can talk about this fast. So the last thing I want to talk about is galactic morphological structure, which is what can these H2 regions tell us about the morphology of the Milky Way? People have been doing this for a long time, trying to fit spiral arms to the distribution of stuff in the galaxy. Here on the left is some work by Ku et al. In 2017, looking at the distribution of neutral hydrogen in a face-on view and comparing it to these the spiral model from Reed et al. Based on the major parallax sources. Here on the right is another paper by Hao and Han in 2014, where they were doing something similar, comparing spiral models to the distribution of a bunch of things like H2 regions, giant molecular clouds, and then of course the major sources. Typically how people approach this problem though is they transform their data into a face-on view of the Milky Way and then try to fit a spiral model to that. And unfortunately for H2 regions, which is what I'm interested in, distances are hard. And so getting the distances to these nebulae is challenging. And so actually doing this in a face-on view is impractical. And so my idea here was that maybe we should try to approach this problem in longitude velocity space. What can we learn about galactic spiral structure or galactic morphological structure just using this diagram here on the left, which is the LV distribution of all of the H2 regions that we found. So if you want to fit a model, if you want to fit, for example, a spiral model to this distribution, you need to be able to write down a likelihood function. You need to be able to write down something that you're going to maximize to show that this is the best fit model to your data. And this is kind of getting into the weeds here, although it's important for the point, which is that writing down that likelihood function, writing down this model for the distribution of points in this longitude velocity space, given, for example, a spiral model of spiral structure, is non-analytical. And here I'll just show you an example of why that's true. So imagine, this is what a one-dimensional spiral looks like through the Milky Way, or this is 4 spirals, in fact, color-coded here. If you start adding some scatter, so you say there's going to be a little bit of scatter in the velocity direction just because there's random motions internal to the H2 regions, that adds a little bit of scatter here in the velocity axis. But then also, spiral arms aren't these one-dimensional things that permeate the galaxy. They have some width. You could think of them as like tubes going around the galaxy. And so that's going to add some scatter in the longitude direction as well. So now you've got scatter in two directions. You have these curves that just trace out this really awkward geometry through the LV plane. And what ultimately that comes down to is that the likelihood function that you need to solve this problem, to fit a spiral model to the LV distribution of H2 regions, is non-analytical. Try as I might, and I did this, for a whole year during my PhD trying to figure this out. It's just, I could not do it. And so we need a new tool to approach this. So that's when I kind of shelved this project for a long time until I discovered this new tool called simulation-based inference, which is a way to derive a likelihood function, not analytically, but using a neural network. You essentially simulate a bunch of data from your model, which is easy to do in this case, and you train a neural network to learn the relationship between the model parameters and the distribution of data in this parameter space. And so here, just quickly, this is a simulation or an example of this simulation-based inference, where on the left panel here is a simulation of a model where I've chosen all the model parameters. And then I've trained this neural network. And then the right panel here is what the neural network thinks that these data should look like based off what is learned about the model. So it's a little nuanced here, but these data here in this second panel are predicted by a neural network that has no idea what galactic structure is. It just has learned the relationship between some simulated data and the model parameters. Similarly, on the right here is showing the likelihood function. So this is the true likelihood function that I calculated numerically, and it took forever. It was completely computationally intractable. And on the right is what the neural network has learned for this likelihood function. And so you can see it puts some power in places where it shouldn't, but the peaks of the likelihood function are certainly looking very good. And then here's a little animation showing as you change one of these model parameters, this is just the viewing angle of the spiral. You can see that the neural network does a good job of replicating the true likelihood function, no matter what parameters you choose for the model. And so now suddenly we have a way to calculate the likelihood function, which was this missing puzzle piece that we needed in order to fit, for example, a spiral arm model to the distribution of H2 regions in longitude velocity space. And so I'm really excited. This is the project that I'm working on currently, and I'm really excited to see what happens and what we can learn about galactic spiral structure with this new neural network tool. That's it. Let me just summarize, some take-home points here, and just, tell you H2 regions are awesome tracers of galactic structure for a whole bunch of reasons. And I think understanding galactic structure is important for models of galactic formation and evolution. And H2 regions really are complementary to other tracers. So for example, we're getting the zero age metallicity with H2 regions, where stars are telling us something about the history of galactic chemical evolution. Over the past 10 years, we've more than doubled the number of known H2 regions. And now we can really start to do some cool projects with this, flux limited sample of H2 regions. For example, trying to constrain the velocity field of the galaxy, the chemical structure of the galaxy, and maybe even the morphological spiral structure of the galaxy. Thank you so much.
Wow. All right. Thank you, Trey, for that just tidal wave of information. And I have to say that neural network model is truly impressive.
I agree. Thank you.
Right. So we are technically past the hour. So if anybody does need to leave right now, feel free to. You can always contact Trey in the future if you have any questions for him. But otherwise, by all means, unmute yourselves if you have a question. Looks like Ryan has the first one.
Yeah, Trey, thanks. Good talk as usual. So could you go back to the slides where you're doing this interpolation to kind of get back on velocity field, and maybe just explain a little bit more how that works? Because it seems like maybe it's kind of spurious, but it seems like you're filling in parts of this diagram where you have very sparse coverage in terms of the data. I'm just wondering how that works.
Yeah, definitely. So the interpolation method that we're using is called kriging, which is a Gaussian process regression algorithm, is like the technical details. Basically, you're not interpolating between the points, you're interpolating the spatial fluctuations of the data. It's kind of a really interesting tool. And you're right, here in the outskirts of the galaxy, there aren't any major points that actually constrain the model. And so when we apply these results to the kinematic distance method, for example, we limit the part of the galaxy where we actually use these data. And so you could imagine drawing a box or a perimeter around the major points, only using this map within that zone. Everything out here is basically, too hand wavy, and we'll just ignore that. Yeah, so that's a fair point. You get something similar when you look at, the spatial distribution of the chemical abundances, for example. Out here in this part of the galaxy before our southern surveys, this is completely unconstrained and unbelievable, and you should probably mask it out or something.
Cool, thank you.
Yep.
All right.
See, Will has his hand up.
Yeah, go ahead, Will.
A question about your last slide or your model. So you showed there for one spiral arm, looks like. Have you done this with multiple? And if so, is it able to differentiate between sources in one arm versus another?
Yeah, I didn't go into the details. This will ultimately be a Markov chain Monte Carlo simulation that we'll run to try to constrain this. And the way the neural network works is that it knows about a single spiral. I've trained it on all these model parameters for a single spiral. But then when we fit it to the data, we can then try it with 0 spirals. You know, you can just have a radial distribution of H2 regions or something. You can try it with 2 spirals or with 4 spirals. And so you're just adding in multiple of the single spirals that all have slightly different parameters, for example. And so one of the cool things about this approach, you know, taking it from a Bayesian approach, is that we're going to be able to do model comparison. We'll be able to quantitatively say if the H2 region data prefer a 2-arm spiral or a 4-arm spiral, or maybe a 0-arm spiral. And, you know, just a radial distribution of, you know, exponentially falling off distribution of H2 regions might be good enough. Who knows? For the first time, we'll be able to put a number to that.
All right. Looks like we could have time for 1, maybe 2 more questions, if anyone would like to ask. Okay, well, I'm not seeing any takers at the moment.
Jesse?
So, yep.
Hi, this is Mark.
Hey, Mark.
So I'd like to ask one. Hello, Trey. How are you?
I'm doing great.
Great talk. Very nice to see you again. Trey, I just wondered, what are the closest stellar tracers that would be doing the same sort of thing? Particularly, you know, I'm aware of a lot of Steve's work with the apogee data, which are pulling up things like warps and other velocity fields. Now, obviously, as you said at the beginning, this is a very different group of objects, but I'm assuming that complexities to do with like non-radial motions and warps and so on might be influencing your model fitting. And I'm just wondering, can you go to another group, another population of tracers that other people have worked on and then synthesize the two together?
Yeah, definitely. And that's basically where this project would go next. So the model is definitely including things like the warp and stuff like that. And in terms of, you know, the apogee data, that, you know, the red giant stars, there's definitely a lot of synergy there. I think the most synergy probably comes from the young stellar population. So correlating these data with the O stars and open clusters and stuff like that. The problem there is even with the distances provided by Gaia, you can't peer too far into the galactic plane. And so you're really limited. This is, you know, getting this global view across the entire Milky Way galaxy, you can really only do in the radio. And so that kind of starts to limit your sources. I think apogee gets pretty far. And so there's certainly some synergy there. And I'm excited to explore that into the future. Yeah, definitely.
Great, thanks. Thanks.
All right. Wow. Those are some excellent questions. And I think unless someone else is dying to ask, we should probably wrap things up in case people have other things that they need to get to. But still, thank you again, Trey, for managing to make your way here just in the nick of time. And
yeah, thank you. Thanks for the invitation to talk. And it was nice to see everybody.
Absolutely. It was great to hear from you on the topic. And for those who are interested, next week we will have Jack Orlowski-Scher from University of Pennsylvania speaking. So everyone take care. Have a great day. Once again, great to hear from you, Trey.